Hello everyone, my name is Lee Kai-ming and now I am going to present my coursework 1 report for the course of Analog and Digital Electronic 2. First of all, the objective of the coursework 1 is design and construct a filter that can accept the signal having frequency from 0 Hz to 1 kHz only. You must use op-amp IC in your filter circuit and any type of op-amp circuit are free to use. The circuit configuration is free to design but we should not include programmable device which is microcontroller component and having a module of circuit that direct purchase from the market. Now I'm going to talk about the design procedure of this circuit. So for my circuit I will use active low pass filter with amplifier. The reason of using active low pass filter because it can accept low frequency components and deny high frequency components. Besides that, it also providing a low frequency signal to the input of this amplifier which operates as unity gain output buffer circuit. It also have higher output voltage can be obtained by changing the gain of the circuit. And last but not least, the active low pass filter only consists of resistor and capacitor, and this type of circuit also known as RC circuit. In order to get the value of the resistor and capacitor, we can use the formula of Fc equal to 1 over 2 pi Rc. The Fc represent the cutoff frequency of the circuit, and the DC gain of the circuit can be calculated by using the formula 1 plus R2 equal 1 plus R2 divided by R1. So the R2 and the R1 can be seen and at the right hand side of the figure. Besides that, we also can calculate the voltage gain, which is AV of the circuit. Voltage gain equal to V out over V in, or equivalent to AF divided by square root of 1 plus bracket F divided by FC squared. So F represent the input signal of the frequency and FC represent the cutoff frequency as mentioned just now. And the AF will be the pass band gain of the filter or the DC gain, which is 1 plus R2 over R1. And in order to obtain the gain in dB, we can use the formula of 20 log AV or 20 log VR over V in. So to verify the circuit whether the output voltage is correct or not, we can use the formula as stated below. During the low frequency, which is when input frequency lower than the cutoff frequency, V out will approximate to V in. V output voltage will be approximate to gain multiplied by V in. During the cutoff frequency, which is input signal same as the cutoff frequency, output voltage will be equivalent to 0.707 multiplied by the gain and multiplied by the V in input voltage. And during the high frequency, which is cutoff frequency bigger than the input signal, the output voltage will be lower than the input voltage multiplied by the gain. So this is the circuit diagram which I built on the breadboard, and from the diagram inside we can show that the component I use only one op-amp, which is UA741 op-amp, one variable resistor, one capacitor, and two resistor. So the two resistor will be represent the R2 and the R1, then the variable resistor and the capacitor will be represent the RC circuit. And I have stated clearly that all the wire, how I connect it to the power supply, oscilloscope, or the function generator. So this is the simulation result I built on Proteus. So for the value of the R and the C, I can obtain by using the formula stated in front just now, which is Fc equal to 1 over 2 pi Rc. So I will fix the value of the capacitor because in practical the cutoff frequency will be not as accurate or as what the value we needed, so we need to have either variable capacitor or variable resistance in order to change the value to get the cutoff frequency to the value that we needed. So in this circuit, I will fix the value of capacitor to be 0.47 microfarad, and after do the calculation, I found out that the resistor I needed is 338 ohm. Then for the DC gate of this circuit, I will just set it to 2, because this is the minimum, this is the easier uh, gain and the value that I can be calculate. So I will just set the R2 and R3 resistor to become 1 kilo ohm. And for the for this, the formula state at the left hand side, XC equal to 1 over 2 pi FC, and V out equal to V in over R plus XC multiplied by XC. This is the formula that used to calculate the output voltage and the power factor of the voltage. So in the simulation result at the top bottom, I mean at the right hand side of the bottom, the yellow graph will be represent the output voltage and the blue graph will be represent the input voltage of the circuit. Then from the formula at the left hand side, after verify, we can know that the result obtained is correct. Then this is the simulation result of the frequency response curve or plot in Proteus. So as you can see, there is a pink purple line. I have moved it to 1 kilohertz, and from the left bottom we can see that the frequency is 1 kilohertz, and at the right bottom the R2 is 3 dB. So by multiply the dB in 1 kilohertz with the initial dB, we can get 3 minus by 6 equal to -3, which is the gain. So we also know that during the cutoff frequency, the gain of the circuit will be approximate to -3 dB. So the output voltage so the gain obtained is correct. So this is the result of the practical result that I simulate in lab, and the value of the power supply is set to 10 watt, and the function generator will be set to 10 watt peak to peak watt 10 peak to peak wattage, which is equivalent to 5 maximum wattage. So the table at the right hand side will be the result I simulate. So the input, I have insert the input signal for 1 hertz until 10 kilohertz, and the V in and the V out will be the value that I obtain. So that is also the value of ideal V out or V in and ideal gain I calculate in this table, because I need to show the comparison between the idea and the practical results to have a clear reference. Also, this is the frequency response curve for the practical result that I construct on the Excel. So from the graph, it can clearly show that the curve is smooth, and the value and the size of the graph is and the value of the graph is almost same as the ideal frequency response curve shown just now. So the output of the result is correct. And this is I will show some of the picture of the oscilloscope that I simulate in the practical result which in my lab. So this will be the picture for the input signal, 10 hertz input signal. This will be the 50 hertz input signal. This will be the 100 hertz input signal. This will be the 500 hertz input signal, and 1 kilohertz input signal, 2 kilohertz input signal, 5 kilohertz input signal, and 10 kilohertz input signal. In conclusion, above project demonstrate how to design a filter which can accept 0 to 1 kHz frequency. With the same technique applied above, we can design a filter that can accept any frequency by changing the value of RC circuit to obtain the frequency we need. By changing a resistor value which connected to the inverting side of the op-amp, different output can be obtained, as the resistor will determine the gain of the circuit, which is useful when bigger output voltage is needed. Active low-pass filters are useful in many electronic applications, as it can be used to reduce the unwanted frequencies such as noise of an audio application. The above circuits are works under first-order low-pass filter. So in order to achieve better attenuation of sharpness of cut-off frequency, we can add many RC circuit to provide a better output result. Thank you for the hearing of the presentation.